All right, good morning, everyone, and welcome to our online training presented by Dlubal Software. Today we'll be working with our FEA and design software RFEM, and the goal of this training is to go over the fundamental knowledge needed so students can model/work with any type of basic structure, view results, and understand fundamental basic theories. For today's training, we will be mostly working and focusing on simple models. My name is Alex Bacon, and I will be your trainer for today. I am a technical support engineer, and I'm joined with my co-organizer, Amy Heilig, who is the CEO of the US office, and a technical support and sales engineer, and we are located in Philadelphia, PA. Here's the control panel. This will be used throughout the training. You can show or hide this panel as well as adjust audio settings. There is a chat box where you can ask us questions. This training is intended for you to just listen, but you can model along with me if you would like. I can't really stop and help you with any specific modeling issues, but with that said, feel free to stop and ask me questions at any time as I am modeling about RFEM itself. Amy will interrupt me when she sees any questions in the chat. Also, just a side note, the model's recording and certificates will be sent out through email, and you can expect that within the next couple of days after this training is over. There will also be 2 breaks. One will be 5 minutes at 11 a.m. and the next one will be 5 minutes at 12. And so here is the content that we will be, or I will be going over, or we will be going through today with today's training. First, we'll start off with going over the principles of FEA software. Then we'll run through a basic introduction of RFEM just to get familiar with the software. After that, we will start with our first model example, which will be the introduction example, and we'll be going over continuous plates. The second example will be the stability analysis, Euler case 1 example. And then from there, we'll create a moment frame out of that fourth example or the second example. And then the last example we will be going through is the concrete model. So just to get started, this will be the first thing we'll be going through is the basics of FEA. So what is FEA? FEA is, well, computer software is based on the displacement method. And why we need to use FEA is because analytical solutions can be difficult when it comes to large, complicated structures. So basically, structures are then modeled and then converted into finite interconnected element meshes. And then the material and cross-section properties are given at each FE node. And the mechanical behavior is transferred between these elements. And basically, the word that I would like you guys to leave here today with is discretization. And what discretization is the process of dividing a structure into an equivalent number of finite elements associated with the nodes. And so basically the workflow for an FEA calculation is the following. So the first step is the determination of the local element stiffness. And then the second step is then the program changes the stiffness relation at each FE node. And this is according to the global coordinate system. Then the third step is to then take the composition of the entire structure. And then the boundary conditions or supports are then defined, and these can consist of sliding, rigid, or hinged. And then the displacement vectors can be determined by solving for the system of equations. And then the last step is to apply the support, or is to obtain the support forces and internal forces from the calculation. So now we can move on to the first example. But before we do that, we should jump into RFEM. So here is RFEM. So this is a basic example that I have modeled before just to allow us to go over the UI and just become familiar with the software. So basically, what is RFEM? So RFEM is a structural analysis software capable of analyzing plates, members, and solids. Deformations, stresses, and internal forces can be calculated on 3D structures, and almost anything is possible to calculate, including volumes. So basically on the left-hand side here, you can see this panel, and this is what we call the project navigator. This is very important for all model data. And when you use this panel, you can see if I have these expanding and collapsible folders, kind of like in Windows. And if you hit one of the pluses, it'll expand the folder. And you can see I expanded the lines folder. And if I go down here to the members folder, for example, if I click on one of these members, you can see that when clicking on them, that this panel is synced with the graphical window over here on the right-hand side, or what we call the work window. We also have tables, so you may notice if you have RFEM open on your end that your tables are displayed down here, and the project navigator and the tables can be displayed or turned off and on with these two buttons up here in the toolbar. So I'll just click this button and my table will pop up. In these tables, you can change data and you can input and delete different data, as well as go through these tabs. And if I go to my cross sections tab, just like the project navigator, this cross sections tab, you can see that the tables are synced up with the graphical window up here. So if you are having trouble locating something in this table, then you can click on it and it'll show you up in the work window. Another thing to note is maybe when you first start up RFEM, this background might be black, or it could be a different color. If you want to change the background of your work window, you can do that by going up here to Options and then Configuration Manager. And within this Configuration Manager, you can change your background from white to black. And we also have an inventor background along with a couple others. Like I said before, this is the work window. So within this window, you can model and you don't have to worry about inputting anything in the tables, and you can just strictly model your whole model within this window using the grid. And we'll be going over all of this more in detail. Up here is your toolbar. So with the toolbar, you can see that it's all organized in sections, and you can right click on anywhere in the gray section that. Like I said, you can right click anywhere in the gray sections, and when you right click, you can see you have a bunch of different options. And for this, I recommend if you first open the program and see that your toolbar is messy and unorganized, you can hit this button here called Reset to Default. And this will reset your toolbar to default, and it will make it look just like mine. Next up here is we have different drop-down menus. The one I would like to point out is the insert menu, where if you go here, you can go to model data, and you can see we have all of the list of model data that you can enter, from nodes to lines to openings. This is very handy if you're having trouble finding the tool you would like to use in the toolbar, because this is just a little more organized. We also then have the file dropdown along with the edit as well. And then up here, you can change your view in the toolbar. So if we go here, you can change it to an isometric. And then we also have the view in the X direction, the Y direction, and then the Z direction. Down here in the project navigator, if we scroll down, we have our add-on modules. And so basically, RFEM is great for calculating internal forces and deformations and support reactions. But if you want to do any design work, you will need these add-on modules to design things like steel surfaces, members according to different standards, such as the ASC and the CSA, but we also have Eurocode and a bunch of other international standards. Next, then we have the display tab down here in the project navigator. So if we go to the display tab here, it looks a little messy and overwhelming, but if we just collapse all of these options here, just like in the project navigator, you will see that all of our display settings are organized under model, loads, results. So for example, if I wanted to hide all my nodes, I could hide all my nodes in my graphical window here, or I could hide things like openings, etc. There's a lot of different customization options in here. The next tab in this project navigator panel is the views tab. And so basically what this allows you to do is to, again, hide different things about your model. So if we activate the visibilities, and then let's say I only want to view, so right now I'm only viewing members by cross-section, and I'm only viewing my rectangular 12 by 12 columns here. That's because I have them selected. Maybe I only want to view my W18 by 50 section, and you see that that will pop up here, and everything else about my model is grayed out. The next tab is the results tab, and you can see the results tab is not here, and that's because we have not ran our results yet. So that tab will pop up when your results are ran. So if I activate my results, you'll now see this tab will come up, and then you can see my results are organized here, and I can activate. Right now I have my members and my axial internal forces activated. I also have my basic internal forces activated for my surfaces. So this is the tab that you will be using to show what results you want to see. But we'll be going through all of this, like I said, in detail later. This is just a quick overview. And then the last thing I want to show you before we hop into the continuous plate example are the controls. So basically, controlling within this work window, you can use your mouse for everything. If your mouse has a scroll wheel, then you can use the scroll wheel to zoom in and out of the model. And you can also rotate the model with the scroll wheel by holding Control on your keyboard. And then while holding Control, if you press in the scroll wheel, you can rotate your model like so. And then also you can use the scroll wheel by just clicking it to move your model and translation. You can also, if you don't have a scroll wheel on your mouse, you can use the keyboard. So if you hold Control and use the arrow keys, you can rotate your model with the arrow keys when holding Control. And you can also move your model left and right and up and down in translation with the arrow keys. And then you can use the plus and minus buttons to zoom in and out. One last thing is we also have this tool up here called Move, Zoom, Shift, and Rotate. And you can move your model around, and you can hold Control, and you can just use your your left and right click, or mostly your left click to do this. So now back to the PowerPoint. So this is the continuous plate model that we will be going over. And basically with this continuous plate model, this will be the example. You can see a continuous plate will be modeled, and then we are going to compare the moment results with a continuous beam. And you can see that continuous beam on the very right-hand side. And so this should be pretty interesting. So now we can hop back to RFEM. And we can begin to model this simple model. So right now I have this model open, and what I can do to open a new model is to go up here to my button here called New Model, or I can also go up here to File and hit New. And then once I go to File or New or hit my New Model button here, I can open up the New Model General Data tab, and then I can name my model. So I'll just name this continuous plate. And I'll just put training November 10th. And then you can see we entered the model name. You can also enter a description if you'd like, but this is optional. You don't have to enter a description if you want. You can see down here the type of model is a 3D model, but if maybe you're only modeling a frame, you can just have one lie in the XZ plane, and you can model something in the XY planes as well. For now, we'll keep this as 3D. And then this next option here, the classification of load cases and combinations. So basically, with any standard, you can have the program create combinations automatically for you. Right now, for this example, we will just be leaving this as none. We won't be modeling according to or creating load cases according to any standard. And then down here, you can set your positive orientation of your global Z axes to upward or downward. And then this button here, this details button, is the orientation of the local Z axes of any member or surface, or basically any element. This I recommend always keeping as downward. So we'll keep that and we'll hit OK. And then basically that is all the general data that is required to be filled out before creating a new model. One more thing I would just like to mention is I will be working in imperial units for this training, but you can also switch or change your units by going here to this button down here. And I can click on that. And then these units and decimal places, this can be changed at any time throughout your model. So if we wanted to change from imperial units to metric, all I would do is go down here to this load save profile, and then I would go up here and set metric as my default, or I could just double click it, and then all of my units for my model will be in metric. I'll change it back to imperial, and then I'll click OK. And now I'll click OK again. And then once I click OK, the new model will be opened up. And you can see now I have a blank work area with my blank grid here set in the XY plane. And basically the first thing we wanted to do is to create a rectangular surface. So I can use my scroll wheel and my mouse and keyboard to rotate this grid plane. And basically this grid, you can see that I have these grid points here, and I can use these to draw my surface. And each one of these grid points, since I'm in imperial units, is 1 foot by 1 foot. And this whole grid plane here is a finite 50 grid points by 50 grid points. And if you ever need to edit or change this grid plane, you can go up here to the button here called Settings of Work Plane, Grid/Snap, Object Snapping Guidelines. If I open this, I have a bunch of different options here. Mostly if you need to change the size or the spacing of your grid plane/grid points, you can go here to spacing, and you can see I have mine at 1 foot by 1 foot. And then also under here, number of grid points, you can see mine's 50 by 50. You can also change this to change dynamically according to what you're modeling, which is nice. You don't have to worry about the size of it then. So now back to modeling our continuous plate. So basically, what I want to do is just model a concrete slab or a concrete surface here on my grid. And to start doing that, I can go up here to my new rectangular surface button. Or like I mentioned before, if you have trouble finding what you need in this toolbar, you can go up here to Insert, Model Data, and then I could just go down here to surfaces, and then I could go to plane, and then graphically, and then I could select rectangle. And you can see we also have a drop down here for a bunch of different other shapes for a surface, along with you could create your own boundary lines for a surface as well. But I'll just go back here and I'll click on New Rectangular Surface. And then you'll see that this box will pop up, this dialog box. And within this dialog box, we have our material. So right now, for some reason, it's set to a default of steel, but I want this to be concrete. So what I'm gonna do is set my material by going to Import New Material from Material Library. You can also create a new material, or if you have the material set but you need to edit it, you can edit the material here with this button. For now, I'll just go to Import from Material Library. And this is the material library that is used throughout RFEM for basically everything. And up here, you can see we have our filter panel on the left-hand side. And what I want to do is I want to filter to concrete and then normal concrete. And for this example, I'll just be using the American standard, the ACI, but you can see that we have a list of other standards you can choose from for your material. And then I'll just choose the latest standard. And basically I'll just be choosing 4000 PSI concrete for this example. And now you can see that our material is set for concrete. And then the next thing that we have to do is basically just set the thickness of our surface. So this surface is going to be 12 inches. I'll click OK. And now you can see that my cursor has changed to this reticle basically. And with this, I can left click anywhere and choose where I want to put my first corner of my rectangular surface. I'm going to set it at 0, 0, 0, the origin. And then I'm just going to draw this, and this surface is going to be 16 feet by 32 feet. So I can look at my coordinates here, and I can make this 16 feet by 32 feet. And then I can left click and set where my top right corner is going to be. And now you can see that this gray surface has been drawn in our XY plane. And basically it's gray because it's concrete, and you'll notice if you draw steel or aluminum that they each have a different color depending on what material you use. So now that that surface is drawn, we can create a second surface right above this one. And instead of having to redraw this surface, I can simply just highlight it. And then I can go up here to my move and / or copy tool. So I'll click on that. And basically I just want to make one copy of this surface. And I just want these surfaces to have a 5-foot gap in between them. So I'm going to move this surface 37 feet in the Y direction, the global Y direction. And again, with this tool, I'm going to make one copy, and the displacement vector is going to be 37 feet in the Y. So I'll click OK. And I actually want that to be not 37 feet, I want to be 21 feet. There we go. So now we have our copy of our surface, and they are 5 feet apart from each other. So now that that's set, I just want to create one more surface. And just as an example, I can simply, instead of using the move and copy tool to create another surface or a duplicate, I can drag from left to right. And then I can, if I hold in Control and then I use my left click, you can see that when I drag this surface, that I can drag it, make it 5 feet from the other one, let go, and then it'll make a copy. So you can drag things around in RFEM and move them, but if you hold Control and then drag them, it will make a copy of the element that you highlighted. So now that I have my 3 concrete surfaces here, the next thing I want to do is just move these surfaces into the center of my grid here. So I'm going to drag from right to left to highlight my surfaces. And then I just want this to be at the origin. So I'll move them down, and then we can simply draw our continuous beam here that is going to be above these surfaces. So what I'm going to do is basically create a new member. So drawing and creating a new member in RFEM is kind of the same as drawing the surfaces. What I'm going to do is go up here to this button called New Single Member. And when I click on that, just like these surfaces, RFEM's asking me, okay, what is the cross section and what is the material of this new member that you want to draw? And basically, we don't have to worry about the member type. Beam is good. You always want to choose beam if you're drawing a beam or column. Rotation, we don't need to worry about. The main thing we want to do is go to cross section. And under cross section, member start, we want to go over here. And this button should look familiar. This will take us to, instead of the material cross-section library, this button will take us to what is called the cross-section library. So I want to click this to choose my cross-section. And once this pops up, you can see I have a bunch of cross-sections to choose from, and they're organized by rolled, built-up cross-sections, parametric thin-walled. But we want to focus on parametric massive sections because we want to basically draw a member that replicates these surfaces. So we want to draw a rectangular concrete member. So I'll click on rectangle, and then with this, I can basically just tell the program, okay, I want a base of 40 inches, and then I want this to be a height of 12 inches, so it replicates that 12-inch thick surface that we have, and then the width. So then I'll go to material here, and I can choose the 4,000 PSI concrete that I created when I drew my surfaces. And now everything is set, so I can click OK. I can click OK again. And now you can see again my cursor has changed, telling me that I can now draw on my grid here or in my work plane here. And you can see this box will pop up here where I could use coordinates to draw out this member, but I'm just going to draw it manually. And it's going to be 5 feet away from this surface. So I'm going to draw that right here. And you can see that my cursor snaps to these grid points, which is nice. So you can make sure everything is spaced out equally. So I'll snap to this grid point here. I'll left click, and now you can see that I'm drawing out my member here. And I'm going to make it the same length as my surface. I'll left click again. And now you can see that that cross section and the member has been rendered out in RFEM. So now you may be wondering, what's the difference between this member here and the surfaces here? So basically, surfaces are 2D elements, and they're comprised of boundary lines. So if I go up here to this button, right now it says solid transparent display model. This is the render button. And if I hit this drop down arrow next to this button, I have 3 different options for rendering my model in RFEM. One's called solid transparent display, one's called solid display model, and the other one's called wireframe display. If we just go to wireframe display real quick, you can see that this member that we drawn, basically what you saw was just a render, and every member that's drawn in RFEM is just a line. Basically, it's just a 1D element. And then you can see the surfaces are 2D elements with this dotted line telling you that it's a surface. And then you also have your boundary lines here that comprise the surface. So if I click on this button again, and I'll put the rendering back in solid transparent, we can now move on with creating or dividing our lines here. So we can add a midline to our plates here. And to do that, basically to divide a line, you can just right click on the line. And when I right click on this line, you'll see that my shortcut menu pops up here. And there's a lot of different handy options in this shortcut menu, but the one we want to look at is called divide line. And then under divide line, you can see we have 3 different options for dividing a line. There's really no right or wrong answer when using any of these options. It's just whatever one you find the most helpful. So just for example, I'll use the option to graphically divide the line. And with this option, basically I'm just hovering over the line, and I'm just going to click and tell it where I want to divide the line. So what we want to do is divide this line at point 16 here, since that's directly in the center. And I'll just click, and now you can see that my line here is now 2 separate lines with a node here in the middle separating them. And now I want to do the same thing for the rest of these lines. So I'll right click here on this next line. And for this one, we'll use n intermediate nodes. And you'll see that I'm using 1 n intermediate node, and I'm choosing to divide the line by a new intermediate node. So I'll click OK. And now you can see that it placed that node directly in the center, dividing the line equally by 1 node. And now I can do that for the rest of my lines. I'll use the 3rd option here, distance. This one's pretty handy if you need to get exactly the right amount of divisions. So I'll divide the line by a new intermediate node. I'll use the true length of this line, 32 feet. And then I just want to basically, I have this set line start and line end set at 50%, which is the exact center of this line. If I change that to 75, if I wanted to put it at the quarter mark, you can see that the line the start and end will sync up, and this will be 25 and 75. Also, if you're ever confused about where the line starts and ends, you can see that there are these black arrows, and these tell you the orientation of your line or the direction that you drew it. So that is handy for tools like this. So I'll keep this at 50. and I'll click OK. And now you can see that this line has been divided and this node was placed right in the middle. So now I'll divide the rest of these lines. I'll hold Control to select multiple lines, and then I'll right click, go to divide line. I'll use distance. You can see that up here, line number, multiple lines were selected, so then I can just keep this at 50% and click OK. And now you can see the rest of these lines were divided. And now we just want to do, lastly, our member. So I'll right click on my member, divide member by distance, and then I'll click OK. So now that these are divided, we basically did this so we can draw a midline here. And to do that, we can simply, instead of drawing in a single member, we can just draw a new line. And then I can draw a line from this node to this node. And then I can right click, and you'll see that we have our line here drawn from this midpoint to this midpoint. And now instead of drawing these other two ones, I can simply just click on this line, hold down my Control key on my keyboard, left click, and then move this line. And you'll see that it's making a copy of the line as I hold Control and drag. And then I'll just do that one more time. And there we go. Now we have all three of our lines here. And now what we want to do is now we can create some line supports. So basically we want to support these separate surfaces here. And to do that, we can go up here to, you'll see that this little section here of your toolbar, if you set it to default, it has the supports. And so basically I'll just go to new line support. And this will look the same as if you used a nodal support or surface support, but when you create a new support, it'll ask you what type of support you want to create. So right now we have some defaults that were created in RFEM. We have hinge support where translation is fixed, but rotation is not. And then we have a rigid support where translation is all fixed and all degrees of freedom, and so is rotation. So for this example, I'll just be using a hinge support, and I'll click OK. And now you'll see this little icon will pop up next to my cursor telling me I can apply a support to any of these lines. So what I can do is just simply click on these lines and add in my supports. So I'll just click on these lines, and then you can see that my supports here have been added and they're supporting the entire length of the line, and they are able to rotate, but they are not able to move in translation. So now
hey, Alex, we have a quick question.
Yeah.
One user wants to know, if you don't want to use one of the default line support types, how can you create your own definition?
Yeah, perfect question. Yep. So basically, if you don't want to use any of the hinged or rigid default supports, you can create your own support definition by clicking on this button here called Create New Type of Line Support. So I'll click that real quick just to show you. And you can see that you can have anything fixed for translation. So basically, these are the translation degrees of freedom and then the rotation down here. So if I didn't want the X direction or the local X direction here to be fixed, I could release that, or I can have it fixed. So you can adjust that for all 6 degrees of freedom here. You can also add in spring constants, and then a little more complexity can be added, such as nonlinearities as well. So yeah, that's if you want to create your own support definition.
Perfect, thank you.
You're welcome. Yeah, so the next thing we want to do is add supports to our continuous beam here at the very end. So what I'm going to do is create new nodal supports. So instead of line supports, I'll go up here to this button called New Nodal Support. And then under here, this looks just like the line support dialog box. And for this continuous beam here, basically, I'm just going to use hinge supports for the start and the midspan. So I'll click OK. And then for this start, I'm going to use this hinge support, and I'm going to use a hinge support at the midspan. But we do need to create a separate support for the end of the beam here. So I'm going to create a new support. And basically this is going to be a hinge support, but I want to fix rotation about the local x-axis. So I'll fix that, and then I'll click OK. And the reason that I fixed the rotation about the x-axis for this beam is because if I didn't and I kept rotation released for all degrees of freedom, the program would think that this beam is rotating infinitely about the local x-axis. So if I right-click on my beam here and I want to view my local axis system, I'll activate that, and then you can see what that local axis system looks like. And if I didn't lock that rotation about the x-axis, then an instability would be caused in the program. So that's why that's locked there. So I'll just right-click again, and in the shortcut menu, I'll turn off the local axis system or the display of it. And now our model is supported for all of our plates and our beam here. So now basically the next step we want to take is to add in the loads. But before that, I just want to ask a few questions. So I'm going to jump back to the PowerPoint real quick. So the first question is, what is discretization? And here are the answers you can choose from. And so I'll just give you guys a minute to think about it. And if you want to, you can put your answer in the chat. And then I'll just, take 30 seconds, and then I'll just go over the answer to this question. All right, so it looks like some people are saying A and some people are saying C. So again, the question is, what is discretization? And basically the answer is A, and it is when a structure is converted into finite elements. So, and some people were saying C, the submeshing of finite elements into smaller elements. So yeah, the correct answer is A, and discretization is when you take a structure such as a building or any type of structure and you model it in a FEA software, and then basically those elements or the structure is converted into finite elements for the analysis. So then the next question I just want to ask is, what is RFEM? And here are the answers you can choose from, A, B, or C. And again, you can place those in the chat if you would like, and we can then go over that. All right, yeah. So again, what is RFM? And it looks like a lot of people are saying, majority of people are saying B, some are saying A. So the correct answer for this question is B. So what is RFM? It is a 3D FEA program for calculating members, plates, and shells. I could see some people saying A, 3D structural frame analysis program, and the reason this one is incorrect is because RFM can run an analysis on frames, but also plates and 3D solids as well. So not just frames, but yeah. So now we can jump back to RFM and continue with modeling our example. So yep, now the next thing we want to do, now that we added our supports to our model, we want to add in the loading. So to add in the loading to any model, the basic procedure is to first, you need to create a new load case because every load needs to be assigned to a load case in RFM. So first, we can open up a new load case by going to edit load cases and combinations, or we can hit this little arrow here, and we have an option here called new load case. So I'll click that. And then another dialog box will pop up, and this one's called edit load cases and combinations. And right now under the tab load cases, a new load case was created. So this one I'm just going to call test and dead load just for an example. So I'm sure for most models, you would have created dead load, and then an action category can be set. This is mostly important when you're working with for a code and you're creating load combinations. But for this example, it's not too important. But if you do check off this action category dead, you'll see down here we have a box called self-weight, and you can see it's activated, and this is telling you that for this load case that the structure or the self-weight of the structure is being taken into account, and you can see a -1 factor here is placed. For this example though, we do not want to take into account self-weight of our example here, so I'll just deactivate that, and then I will click OK. And now you can see up here it says test dead load case 1. This is the only load case we have, so when I hit this drop down, we only have one to select from. But now we want to, when we apply our loads, they will be attached to this LC1. So now we want to create a surface load to apply to our 3 plates here. So to do that, I can go up here to new surface load. I'll click on that. And then for a new surface load, basically what you want to do in this dialog box is work from the load type. So we want this to be a force, and the distribution onto our plate here is going to be a uniform distribution, and it's going to be applied from the top down. So that will be our global z-axis, the true area of it. And then now that that's all set, we just want to tell the program what magnitude this loading is going to be. And so this loading is going to have a -210 pounds per square foot, or 0.221 kips per square foot. And I place the negative sign to tell the program to apply it from the top. So I'll click OK. And now it's asking me, okay, what surfaces do you want to apply this load to? And so I can use my cursor here to click on my surfaces here. And now you'll see if I can hit escape or right click to cancel out of that tool that my uniform loading was applied. And you can also see the value of what that loading is as well. So now what we want to do is add a uniform load to our member here. So I'm going to go up here to new member load. And then I'm going to click on the load type. So this looks pretty familiar to the surface loading. I'm going to click on load type. I'm going to have it make it a force. It's going to be uniform. And then again, it's going to be in the global Z axis direction. And then the load parameters, it's asking me what magnitude of this loading or what the magnitude of the loading will be. So I'm going to make this the same basically as the plates. So that is going to be -0.21 kips per foot. So I'll click OK. And then again, it's asking me, okay, what member do you want to apply this loading to? I'm telling it this member right here. I'll right click, and now you can see that my uniform forces were applied.
Hey, Alex, another quick question.
Mm-hmm.
Going back to the member load dialog box,
Mm-hmm.
one of the users wants to know how to apply a load with an eccentricity. So I think you can go ahead and show the detail options next to the force load type.
Oh yeah, yep. Okay, yeah, so yeah, if you want to apply a load with an eccentricity here, you can set, basically, like Amy said, click on this details button next to the force, and then you can set an offset in either the Y, the local Y direction of the member axes, or the Z direction. And you can enter in, right now it's set to inches, how much you want to offset that loading. And then down here, it's basically asking, okay, what relatively to where on this cross section do you want to offset that loading? And you can see when I click on either of these directions here, I can have it offset from the center, the direct center, the shear center of the cross section, or the top of it, etc. And you can do that for the member start or the member end, basically.
Okay, thank you.
You're welcome. Yep. Yeah, so actually, let me make sure that's, yeah, okay. Yeah, so now to move on to, let's see. The next thing we want to move on to, or to talk about, the next topic is basically FE mesh refinement. So just a quick overview or background. So basically these surface elements, I'm going to toggle off my loading real quick. You can show or hide your loading by clicking on this button up here called Show Loads. So I'm going to click on that. But basically, FE mesh refinement. So if I go up here to calculate and I hit generate FE mesh, this is normally done automatically when you run your calculation, but just for example purposes, I'm going to generate it just so we can see what it looks like. And looks like it might be turned off. Let's see. Oh, there we go. Yeah, so FE mesh and an FEA program, this is the FE mesh that's generated, and this is how your results are basically calculated at they're calculated or ran at FE mesh point. And what a refinement does is it'll shrink this FE mesh to basically give you more accurate results, but also increase your calculation time. So what I want to do is, for all surfaces, I want to apply an FE mesh refinement, and I want to show you basically how the results change depending on the size of your FE mesh. So what I can do is I can turn this back to a solid transparent or just a solid rendering, and I can add an FE mesh refinement by, you can do this by right clicking on the element you want to add the FE mesh refinement to, and then going to FE mesh refinement and then new. Another way to do this is, for example, you can use your project navigator here on the left-hand side to add in different input data. So we can go up here to this folder called FEMesh Refinements. I can right click on that and I can select new FEMesh refinement. And with this, I want this to be a surface refinement. And for this first surface, I'm going to make it the smallest FEMesh refinement of 0.2 feet. So I'll click OK. It's asking me what surface I want to apply this to. And it's saying surface number. And I can click on this here to select the surface I want to apply it to. So I'll select surface 1. And then I'll click OK. And now it deleted my FEMesh. And if I go back in here to generate FEMesh, you can see how much smaller my FEMesh elements here are to the basic FEMesh that was applied globally in the beginning. So I'm going to apply 2 more FEMesh refinements to the last remaining 2 surfaces. I'm just going to right click and go to FEMesh refinement and then go to new. And basically when I do this, I want to create a new FEMesh refinement. And I'm going to make this one 0.4 feet. I'll click OK. And then the last one I'm going to make 0.6 feet. And this will allow us to get a nice visual when we produce our results to see how the results change depending on the size of our FEMesh here. So I'll make this one 0.6 feet. And now that our FEMesh refinements have been created, what we want to do before we produce our results is create a section cut through our plates here. And this will allow us to get a nice diagram or visual of the internal forces of our plates. So if you want to create a section cut within your model, you can go up here to define section and result diagrams. And then you can create a section numerically. And this is the new section dialog box. So it's asking me, okay, what section name do I want to make it? I'll just call it AA. I want the section to go through surface, and then section type will be via plane. And then I just need to tell it, okay, where's the section starting and ending? I can enter those coordinates manually here, or I can just go to select the edge points of the section. And you can see we have a lot of different snap options in RFEM, just like in AutoCAD, where you can select the midpoint and my cursor will snap to the midpoint of that line. And then I can just have my cursor snap to the other midpoint. And basically, this is all we need to add. And it knows what plane we want the section cut to be in, because right here you can select the local and plus or the positive Z plane. So we'll keep that set. And now we can click OK. Now we have our section here, and we'll get a better understanding of how this section works once we run our results. And now, instead of having to recreate that section for the last 2, I can again hold my handy control key here, left click, drag. Oops, let me just select it and then hold control, and then drag, drop. And I created a copy of my section there. Again, I'll select it, hold control, drag, drop. And this is a pretty great workflow for RFEM, holding control and copying things instead of having to recreate them. So now you'll see that my sections, or hopefully you can see that my sections have different names. And if I want to change those names real quick, I can go to my project navigator here and look at my model data, scroll down, and I can find the sections folder. If I expand that, you'll see we have AA, AA1, AA11, and I can change these names if I want to by just editing them. So we would want this to be AB, and then we would want this third one to be AC. So great, yeah. Everything is basically our whole model here is ready to run the calculations. We have our supports, we have our loading applied. So now the last thing to do is to run the calculation. So to run your calculation, you can go up here to calculate and calculate all, or you can use this button in the toolbar just called calculate all. So I'll click that. And then once I click that, RFEM will take about, usually depends on how large your model is and how refined your FE mesh size is. But for this smaller model, it shouldn't take too long to run through the calculations since we only have one load case as well. So right away, you'll notice that our results have ran, and right now we are viewing the global deformations of our plates here, along with the global deformation of our member here, which might be a little hard to see, but that's signified using a yellow line. I can also, for a cleaner look, I can go down here to grid, and I can make my grid disappear, and now we get a better view. So yeah, like I said, the global deformations, we have our results tab here that I talked about in the beginning that came up, and we have our global deformations checked off. And then the next bit of information or results we would like to view, maybe our member results. So I'll click on member, and then maybe we want to view, I don't know, the axial forces of our member, which we don't have any right now, but if we want to view our moment about the y-axis of our member here, you can see that that moment diagram is displayed directly on top of our member, and we have a maximum moment of negative 6.7 kip feet, and then we have our positive moments down here. We can also then view our surface results by scrolling down here to surface and then checking off surfaces so we can view the internal forces of our, whoops, sorry about that. So we can view the internal forces of our plates here. So now that I have the surfaces checked, I can check the moment along the x-axis. And this is the basic internal moment, like I said, along the local x-axis. And every element has a, like I said before, has a local axis system. And this is what the lowercase, if you ever see the lowercase letter within RFEM, this is referring to the local axis system, which you can see when I hover over the surface, you can see this. And then the capital letters refer to the global axis system. So in order to see the results better, I can activate the sections that we created by scrolling down here and going to checking off sections. And then once I check off sections, you can see that the basic or internal forces, the moment along the local axes, is displayed as a diagram in this section cut, and that will allow us to compare these results to our continuous beam here. And now you can also maybe see a difference in the accuracy between the plates with the different FE mesh sizes. So you can see that this one has a finer diagram, and the value here, the peak moment, is a little bit different, off just by a little bit from the rest of the plates. And now I think it's a good time to mention like I said before, the size you pick for your FE mesh affects your results. So to go over this real quick again, if you go up here to calculate, and under the global calculation parameters tab or button here, if we click on that, I'll open my global calculation parameters. And something I want to talk about for our next topic here is you can turn off the activate shear stiffness of members under the option here. So again, I'm under the global calculation parameters options, and there's an option here to check on or off activate shear stiffness of members. And this is really important because if you're trying to compare your hand calculations to RFEM or basically any FEA software, RFEM is always running calculations with the shear stiffness of members considered. So once this is done and I uncheck that, you will have to recalculate. If I hit OK, it's asking me this action requires that all results will be deleted. Do you want to continue? Yes. And my results have been deleted. And if I change this, or if I run my results again real quick, you'll notice that the most noticeable change will be with the bending moments. And once this is done, the bending moments should have changed a little bit, and this is because basically the methods used in school or in class assume an infinite shear stiffness when in reality there are some shear deformations happening when the member bends. So definitely keep this in mind when comparing hand calculations of deformations with RFEM. And now to go back to the PowerPoint, we are going to go over and compare two plate theories. So basically, to help you understand, I will use beam element theories as an analogy. So the first theory we have is Bernoulli's, and then the second theory we have is the Timoshenko theory. And we're going to compare these. And so basically the assumptions that are made for Bernoulli's is that all cross sections remain in plane and perpendicular to the member axes. And with this theory, there is no consideration of shear deformations, and there is a completely rigid shear stiffness. And with the Timoshenko theory, again, same assumption for Bernoulli's, the cross sections remain in plane and perpendicular to the member axes. But with this theory, shear deformations are taken into consideration, and the shear stiffness is limited and is not completely rigid. So to show a graphic to represent what I just talked about, you can see here that the deformation is perpendicular to the member axes for Bernoulli's simplified theory. But with the Timoshenko theory, here we have an additional angle, so we have additional deformation. And this is due to additional shear deformations and shear stiffnesses. So now that we have those two theories, I do see that we are a little past 11 o'clock, and I did say that we would have a 5-minute break at 11. So before we move on to comparing these to the plate theory, I would just like to give everyone a 5-minute break in case you need to use the bathroom or get something to drink. So we'll come back here, I'll say at 11:15. So we'll take a break then and come back and resume going over these theories. Okay, so let's resume. So I did see there was a question about how to edit the section stiffness for members and for columns, beams, and slabs. So I can just jump back to RFEM real quick and just go over that real quick. So real quick, we can go back to RFEM. And if you need to modify the stiffness for any of your columns, beams, or slabs according to a standard, or you can just set a custom one. So if I go into if I want to edit my member or slab here, I can simply just double click on it. And then we have a tab here called Modify Stiffness. So if I click on that tab, you can see that it's asking me, okay, what definition type would you like to apply? And you can see we have a couple of different standards here, but what you can do is add in your own custom modified stiffness. And you can see that under multiplication factors, you can change the factor for your torsional stiffness, flexural stiffness, axial stiffness, and shear stiffness of your members if the code that you are designing per is not located under here. And again, real quick, you can also just do that for your slabs as well. It's basically the same procedure. You can go and double click on it and go to modify stiffness and then change your definition type here. So just to jump back to the PowerPoint and continue learning about plate theory, I'll jump back here and just to reiterate what I talked about before we took a break was basically Bernoulli's theory takes into consideration shear deformations, or does not, I'm sorry. Bernoulli's theory does not take into consideration shear deformations and assumes completely rigid shear stiffness, whereas with the Timoshenko theory, it does consider shear stiffness as limited and is not completely rigid. And again, graphically, you can see this between the two theories. So now these two theories we can apply to plate elements. So an equivalent analogy for plate elements, we have the Kirchhoff theory, similar to Bernoulli's, but for plates, and a similar theory to the Timoshenko theory is the Risner-Minlin that works basically the same way for plates. So here are the assumptions for the Kirchhoff theory and for the Risner-Minlin theory. So basically these two theories share very similar assumptions. You can see that they both assume geometrically linear small deformations. They both assume a linear elastic material is used, basically referring to Hooke's law. They assume that the cross sections remain flat with no warping, and they both assume a constant thickness for the cross section. But the differences come when it comes to shear deformations. The Kirchhoff theory does not take into consideration shear deformations, where the Risner-Minlin theory takes into consideration shear deformations and also takes into consideration transverse/lateral strains. So we can move on to the next slide and we can take a better look at what transverse/lateral strains means. So here we have one beam, and when a tension force is applied to it along its length, the cross-section will shrink with regards to its height and width. So the factor here is mu, and this is what takes into account this consideration. And so just to reiterate, the Kirchhoff theory and the Risner-Minlin theory, the Kirchhoff theory does not consider shear deformations And it yields great results when using very thin plates, for example, concrete slabs. And you also have to keep in mind that it only considers pure bending, load-bearing capacity, and it's also considered a simplified approach. With the Resner-Midland theory, the results are pretty good for thick and thin plates, and then shear influence component is relatively high for this theory. There's also a significant error when neglecting shear force. This also results normally, or tends to result in a higher value approach, and also produces more accurate shear forces. So in my opinion, the Resner-Midland theory is what you should use, but it is good to know the difference between these two plate theories. So now we can move back to the program and see this in our model. So if we go into, again, the calculation parameters, we can go to calculate, and then, calculate, and then calculation parameters. You will see, again, under these options down here, that the default is set to the Resner-Midland theory for plate bending theory. And remember, so if we take a look at our results here, mostly for, let's say we want to take a look at our results, the shear results for our member here, or we want to take a look at the shear results for our surface. So let's see, we have a peak for this middle one of -2.032 kips. So if we go up here to calculate, calculation parameters, try to remember that result. If we set this to the Kirchhoff theory, which does not take into consideration shear deformations, we can click OK. It's going to ask me to recalculate. We can run the calculation real quick. So now you can see that that peak shear force has changed from -2.032 to -2.124. Didn't change a lot, but this can really add up when you have large, complicated structures. So now back to RFEM real quick, or back to the PowerPoint real quick. I just have another question to ask everyone, just to check and make sure everyone's understanding is okay. So basically, what happens if the question is, what happens if the shear stiffness is activated? And here are the options, or the answers to choose from, and then I'll give about everyone 30 seconds to look over and think about it, and you can also put your answers in the chat if you'd like, and we can go over it. All right, so it looks like a lot of people said A, a couple said B. So the question again, what happens if the shear stiffness is activated? And basically the correct answer is A, shear deformations are considered. So When shear deformations are considered, it's because this means that the member or plate is not infinitely rigid, and additional deformations will occur along with higher shear forces. Then the next question, or this is a true or false, is the plate theory of Kirchhoff does not consider any shear deformations. And this is either true or false, and you can think about it, and we'll go over the answer for this one. And you can also put, again, your answer in the questions. Awesome. So it looks like most of you are saying true. The majority of you are saying true, and some of you guys are saying false. So this one is true. The plate theory of Kirchhoff does not consider any shear deformations. So this theory does consider, if you have this activated, does consider an infinitely rigid shear stiffness, which is normally what is assumed in school, but does not happen in reality. So now we can move back to RFEM, and basically that was the end of the continuous plate example and going over plate theory. So the next model or example we're going to move on to is we're going to get into the Euler case 1 and stability analysis of a frame. So we can hop back to RFEM and begin modeling and going through this example. So again, easy enough, we can create another model. So you can have multiple models open at once in RFEM. So we'll just go up here to the new model button and click on that. And then we'll have the model name. We'll call this one Euler case 1. Training November 10th. And then we can put a description in. This will be a 3D model. We're not going to create any load cases or combinations according to any standard or automatically. Keep everything the same. We'll click OK. And this model is going to be very simple. We're just going to create one single member or column. And to do this, we can go up here again to our new single member button. And the new single member will be, again, a beam type. And we want to create this cross section. So I'll click on that. And this cross section is going to be a I-beam. So this is under our rolled sections, I-beam. Again, when we're filtering through, so we haven't seen this yet. So when you click on I-beam, for a lot of these cross sections, you can pick a cross section from a manufacturer slash standard group. We have our filter over here on the left-hand side. And again, we have American standard, the Canadian standard, along with a lot of other international standards, such as the Eurocode, etc. So for this example, though, I'll just be using the American standard, the American Steel standard, and then the manufacturer standard. I'll choose the latest year. And again, I sections, and I'm under W. So then I'll scroll down here to 12 by 35, just using this for an example. So I'll pick 12 by 35. And then the material, I would like to choose a material from, or import one from our material library. So I'll click on that. Again, so this column is going to be metal, it's going to be steel, and then I'm just going to choose an American Standard, and then I'm just going to choose steel A992, this material. And something I didn't point out earlier is when you select your material, you can see down here, you have your material properties. So your modulus of elasticity, shear modulus, etc., and yield strength, very good to know. So we'll click OK again. Our field has been filled out here, and you can see our cross-section. You can also view info about cross-section or some information. So if I click on this little eye right here, I can click on that and we can get our cross-section properties. This is also very good to know, you know, dimensions, shear area, moment of inertia, etc. Great to know. So we'll click OK. And now basically we're going to draw our member like we did before. And let's say I wanted to draw my member perpendicular. I'm drawing a column. If I wanted to draw this member along the z-axis or perpendicular to this work plane, there's two ways to do that. I can either go up here to change my work plane from the XY work plane to the YZ work plane, or I could do the XZ work plane and change my work plane to a vertical plane here. Or I can also simply just go over here to this box and I can choose length and check off this box called length and direction. My column's going to be 30 feet tall, and I can tell it, okay, so I want to draw this perpendicular to my work plane in the positive direction, and then I can simply just draw it or click, tell it where I want the base to go. And again, we can also just change the work plane, and I could just draw it manually on the plane here and just tell it 30 feet high. So I'll draw it, I'll click, and then I'll right click to exit out of that tool. And then I'll add a rigid support down here at the bottom. So another thing I would just like to mention real quick is you've seen me highlight. If you highlight from left to right, the box is red, telling me that I'm only selecting elements that are fully engulfed in this box, such as this origin node here. But if I draw from right to left, anything that touches the box will be highlighted. So this is nice just for selecting objects such as this origin here, instead of having to, you know, click on it. I can just select that real quick. And then I can add a support to the bottom here. Since I already selected my node here, I can go up here to my button, nodal support, and then I can create my support here like we did before. I have my presets here. I can just select rigid. This rigid support will fix all degrees of freedom. I'll click OK, and now that rigid support is added to the bottom there. Now the next thing we want to do, now that our Euler column 1 is created, and the next thing I want to do is go over here to, well, basically we want to add loading to this column. And again, to add loading, we need a load case for the loading to be assigned to. So I'll go here. I can either click new load case, or I could just I want to add a nodal load to the top of this column. So if let's say I don't have a load case defined and I click on some kind of loading, the program will be like, okay, you don't have a load case, so you need to create one before you can add loading. So the dialog box will pop up, and I'll just name this one test, dead load. My action category is set automatically to dead. Again, self-weight for any dead load created is automatically activated. We don't want self-weight to be activated for this example, so I'm going to deactivate it by unchecking that. I'll click OK. And now my new nodal load dialog box should pop up since I clicked it before going in there. And basically what I want to do is add an axial load. So this will be an axial load of -5 kips, and then a lateral load of 2 kips will be applied to the side of it. And you can see in this graphic window down here what that loading is going to look like before you apply it to your node. So that looks good. I'm going to click OK. Oh, and it looks like I had my node down here selected before I went in there. So I'm going to hold Control Z to undo that. I could also, since I made this mistake, I could just simply use the control copy function and just hold Control, copy this to the top node, and then just delete this loading down here by hitting the delete button. And now our loading is applied to our top node here on our column. So now the next thing I want to do is show you something very important. So I'm going to click on Calculate All and run my calculation real quick. And then the first thing again you'll see whenever you run your calculations is the global deformations will come up. And then what you want to do is show the internal forces of this member. So I'll check off members, and then I will check off right now I'm showing the moment. So you can see my moment diagram along this member. I have a max moment of -60 kip feet down here at my base. That goes to 0 at the top. But if I if I set this to view in the X direction, X direction, and then I show the global deformations with the Y direction, and I want to show just the deformations in the X direction. You can see that it's 3.782 inches in this direction. And now I just want to show you how this linear or first order calculation differs from a second order calculation. So this calculation that we ran with this load case was just a simple linear calculation. So if I open up my load case again, if I go to load cases and combinations, generally load cases are based on a first order calculation. So I'm in my load case here. This looks familiar with the general tab, but if I click on the calculation parameters tab, you can see that our method of analysis is set to geometrically linear analysis. And normally, like I said, load cases are based on a first order analysis, and load combinations are normally based on a second order analysis. And maybe you recognize a second order analysis based on the name, P delta or little p delta. So we can change this load case to a second order analysis. And so basically, a first order analysis makes the equilibrium of the beam based on the underformed system, and the second order analysis sets the equilibrium based on the deformed system. So if I again set this to a second order analysis, I'll click OK. The program's going to delete my results because I've changed it. I'll just click on show results. It's saying my results aren't found, so I need to start the calculation. And again, that 3.7, it was about 3.72 deflection, 3.72 inches. Now it's 3.905 inches. So that has increased because of the P delta effect. And if I look at that moment again at the bottom here, it was capped at 60 kip feet. Now it's at 61 kip feet. And this again is because of the P delta effect. Since the deformation has increased, our deformation has increased, this has increase the moment arm for the applied axial load, which again is going to increase your maximum moment. So deformation was increased, maximum moment was increased, so you can understand how changing your calculation to a second order analysis will give you a different result. One quick note, something I'd just like to mention is members in RFEM are determined to be a beam or column based on how the loads here are applied. In this case, we have a column because of the axial force applied to the top. So if you want to draw a column, if you want to draw a beam, just keep your member type here set to beam. This can be used for beams, members, and columns, basically. So don't have to worry about that. And then now we can move on to the next topic. What I want to do is just change the loading that's applied to this column. So I'm going to double click on it, and you can just double click on any of your loading in RFEM to change the load, to change the magnitude. I just want to make this 0. And then I just want the axial force to be negative 0.1 kip feet or negative 100 pounds. And I'm doing this because now we're going to go over an add-on module. And this add-on module is called RF Stability. And basically, as a student, you guys have access to all of the add-on modules that we have in RFEM. So what I can do is, you can see you have your long list of add-on modules here in the project navigator. I have my most recent or my favorites saved. You can right click on any of these and set them as a favorite. So they're at the top here, so you don't have to go rooting around for them. If you have trouble finding an add-on module, you can go up here to add-on modules, and then you can go to stability or any of these, but we're going to go to stability. And I'm going to click on RF Stability. And this add-on module, or all of the add-on modules, look just like this. They're a dialog box, and you stay within RFEM, and the add-on module will pull all the information from RFEM into this module, so you don't have to redefine anything about your model. And basically, what RF Stability does is it uses the help of eigenvalues and different eigenforms to perform a stability analysis. So just some quick background information. Euler was a mathematician who came up with different cases to show the critical factor along with the critical load and lengths. And this is something basically every stability analysis does. And in order to get the different buckling cases, I will need to deactivate the minimum initial pre-stress for cables and membranes. And it's also important, that we go over here under activate division, also for straight members, that we go into edit these settings using this edit button here. And we want to make sure that's activated. And we also want to increase the divisions, the minimum number of member divisions here from 2 to 10, just for this example to get a more accurate result. So we'll click OK. And now I can simply just hit calculate. So you can see that I have my load case / combination. This is the load case that the module is going to pull the axial forces from. So that's automatically selected since it's the only one we have. So everything else we can leave as default, and I can click calculate. And once the calculation is ran, we should get a load factor and a magnification factor. So you'll see that pops up. And basically, the critical load factor is the amount you would have to, this first critical load factor is the amount you would have to multiply the loading in your model in order to get an unstable system. Or it can also be looked at as the total percent of the loads your structure can take. So for this structure, I would have to roughly multiply my loading by 135 for this column to be unstable, and for it to be unstable and not be able to handle the loading. And then next, so that this is table 2.1, critical load factors, table 2.2, effective lengths and critical loads. We have these here, and we can also view our results graphically and look at the eigenvectors. So if I hit the graphics button down here, we can also turn on colored cross sections. So if I go to my display tab, and then I go to results, if I expand my results option here, under the deformations expansion category here, I can click on that, and then I can choose cross sections colored. And now you can see that that yellow line that once represented our deformation is now colored according to well, right now we're looking at our RF stability results. So you can see over here, it's giving us our value or our unit. And at the highest deflection, we have 1. And then you can see how the colors correspond to these separate values. So right now, we're taking a look. If we go, this is the panel that comes up whenever you run your results. It gives you the color scale here. We also have our filter tab here at the very end, along with our factors tab here. So the factors tab for our stability is important because in here we can take a look at right now we're looking at our first eigenmode. We can then take a look at our second eigenmode here, our third eigenmode, and then our fourth eigenmode. But mostly focusing on the first one, I think it's clear that the column will first be unstable, and it's, didn't want to adjust this factor. In its first eigenmode, it's clear that it'll be unstable in the weak axis direction. As you can see, the deformation is in the weak axis of the column. In the y direction, about the local z-axis. And this, so if I turn on my local axes of my member here, you can see that it's bending about its weak axis, about the local z-axis here in the y direction. And again, if we take a look at our cross-section properties, this is mostly because that is the lower moment of inertia value here for about our z-axis. So this is why the column buckles around this axis. And if we choose this button here, we can jump back to the RF stability add-on module.
Hey, Alex, this might be a good time just to ask a couple questions. When you went back into RF stability, one attendee is wondering, why do we deactivate the active minimum initial pre-stress option under the general data?
Yeah, so
I can comment to that. I would say that in this situation, it doesn't matter. We don't have any cables or membranes to consider with this eigenvalue analysis. So whether you activate this or deactivate it, it should not have much influence on this particular design because we just have a typical steel type member. So hopefully that answers that question.
Okay, awesome. Yeah, good question.
The other question is unrelated to RF stability, which you can just quickly mention. Maybe one user is asking how we can consider P delta analysis automatically in the load combinations. So maybe you can explain what's default and what's not for load cases and combinations.
Okay, yeah, I can go over that real quick. Yeah, so basically with the load cases and combinations, with load cases in particular, the default for load cases is always in the program geometrically linear analysis, or is a first order analysis. And with load combinations, I can create one real quick. The default for a load combination is always a second order analysis. And I don't believe there's any way to change this default, but you can always just go into your load cases and change them from change your method of analysis from second order to first order for your load cases or combinations.
Yeah, so I think it's important to know that in the program, all load combinations are automatically generated according to a second order analysis, which considers P delta and P little delta. You always have the ability to change them, as Alex mentioned, to first order. When you're utilizing any type of cable element or fabric membrane within the structure, the program will automatically default to a large deformation analysis, which has to be used for those type of members. So that should hopefully answer that question. So thanks, a little bit unrelated to what you're currently working on, but I think it was a good question. So thanks.
That's all right. Yeah. Yeah, great question. Yep. Thank you, Amy. So yeah, we can get back to, I'll just delete this load case real quick, and we can go back to the auto module. Those are great questions though. So I'll just click OK, cancel out of that. Yeah, so back to RF stability. Again, I was just mentioning the effective length factors. You can find those under the table here, effective lengths and critical loads. And let's see. Yeah, so now I'd just like to show basically what the structure looks like, or what RF stability looks like when the structure is unstable or the loading is too high. So I'll just cancel out of here. And then to switch back to our, you can see up here, we have RF stability results being shown. And if you have a lot of different load cases and combinations and result combinations, you can scroll through those or pass through those using these arrows here, or you can hit this drop down and switch between all your load cases and combinations in this drop down window. So we'll go back to our load combination 1 where we have our loading applied. And then I'm going to just change this loading to something that this column won't be able to handle. So I'll change it from 100 pounds to something like negative 14,000 pounds or negative 14 kips. I'll click OK, and that'll be applied to our column here. And just for example purposes, let's say we go back to RF stability, we changed our loading on our structure. The RF stability results are gone because we changed the loading. So I'll just go down here to RF stability, and I'll double click on that to open it. Right now we have our load case running as a second order analysis. So let's say I hit calculate to check my structure, and an error message is going to pop up, and it's going to say my LC1 results are not available to be run in RF stability. And this is due to my structure being unstable. So I should have shown, so if we run this basic analysis, if I just run the analysis in RFEM to get my deformations and internal forces and support reactions, this is something that's going to pop up if your structure is unstable. So basically it's saying my structure is unstable, there's an instability found. And down here, this message is saying that the specified load is greater than the critical load, and it's possible to calculate the critical load factors in buckling and the auto module RF stability. So basically what I can do is, again, I showed you if I try to run the calculation in RF stability, it won't let me. So the next step would be to go into my load cases here. And the reason why I can't run this load case in RF stability is because I'm running according to a second order analysis. So if I change this to a first order analysis, I'll click OK. And then if I go back into R Stability, I can change this, or I can hit calculate. And now my calculation should be able to run with no error. And once this is done running, you'll see that my critical load factor here is below 1, which is not good. If you see your critical load factor below 1, this is saying that basically your structure cannot take 100% of the loading. It can only take 0.966%, or I'm sorry, 96.6% of the loading. So just to reiterate, if you see a critical load factor below 1, then this means your structure is unstable and cannot handle the loading that is applied. So if we go to the graphics, you can see what that deformation looks like, and that is what an unstable model would look like. So now, next thing, I just have another question just to help with understanding. So if we hop back to the PowerPoint real quick. The question is, the critical load factor specifies which factor can be used to increase the stiffness until the structure system fails. And the question is this true or false? So I'll just give you guys 30 seconds to answer that, and then we'll go over the question. All right, so again, the question looks like most of you answered. Let's see, looks like it's a mixed bag, true and false. So again, the critical load factor specifies which factor can be used to increase the stiffness until the structural system fails, and this is false. So the word here that we want to focus on is stiffness. This should be loading instead of stiffness. So it should be the critical factor specifies which factor can be used to increase the loading until the structural system fails. So yeah, this one is false. So now we can hop back to RFEM and continue with modeling. I'll go back here and we can continue with our Euler case 1 example. And basically I'm just going to save this model by hitting the save model button up here. Side note, when you can save your model, I would save often, but if at some point you have a crash, there's no need to stress because RFEM creates backup files of your model. So if for some reason you haven't saved for a while and the program crashes, this shouldn't be a problem, and there should be a backup file that's created. So now that that's saved, I'm just going to save this model as a copy and click OK. And then I'm just going to name this, instead of Euler case 1, I'm going to make it a moment frame analysis, and I'll save that to my desktop. And then the reason that I'm doing this is because then I can open this back up as a separate model and turn this column into my moment frame. So I'm going to turn off the results and change my force back from -14 kips to a more reasonable load of, let's see, -5 kips again for an axial load. And then what we want to do is make a copy of this column. So I'm just going to highlight it, and then I'm going to hold Control, and just to get a better visual, so I'm going to hold Control, and I just want another column to be 10 feet away, since this is 10 feet spacing for these grids. Now we have our two columns that will make up our moment frame. I'm just going to highlight my nodes here, and I want to change the height of these two columns. And since I highlighted both of the nodes, when I double click on them to edit them, I'm editing both nodes 3 and 5. And since they have both the same height, I can change that height value, or it's showing me that they both have a height of 30 feet. I just want to make this 10 feet, so I'll type in 10 for that Z coordinate and then hit enter. And now you can see that my columns are now 10 feet high. And this will act as our frame, or our columns for our moment frame. And now all we need to do is draw our beam here to connect our two columns. So I'll go up here to new single member. And then I want to create a new cross section, a smaller cross section than my columns. And that cross section will be a W cross section. So under rolled I sections, that will pop up. And again, my filter options are saved from what I previously have done. So I can just scroll down here to 8x15, choose 8x15, change my material to steel A992, click OK. I can click OK again. And now I can simply just select or snap to my node here and then snap to my other node here. And I'm getting a perpendicular symbol showing me that this is all perpendicular. And then I can right click, and now we have our beam connecting our two columns here. And now what I want to do is just add to make this a little more interesting, I can just add a new member load by clicking on the new member load button. And this is going to be a force uniform. It's going to be in the global Z direction, and it's going to be -3 kips per foot. I'll click OK and then apply this. And so now we have our axial loads on our columns and our uniform load on our beam here. And then I can run my calculation real quick just by clicking calculate all. And I do see that it's 12 o'clock or about 12 o'clock. So I think now is a good time to take a quick 5-minute break. So I think everyone can take a break and come back at 12:09. We'll come back. So. All right, so let's continue. So now that we have our results ran, that's what we did before we took a break. We can see right now reviewing our members, or the results on our members, basically our internal forces. Right now we're viewing our moments about the y-axis. We can also view our axial forces, mostly for our columns, and also our shear diagrams as well. We can also get a look at our global deformations, our resulting global deformations. Most of them are coming from this beam, but also a little bit in our columns. We can also take a look at our support reactions down here. So I can activate my support reactions. And we can look at our reactions in the vertical and lateral direction, the x direction and the z direction. And we can also take a look at our moments as well. So I can activate my moments and turn off my reactions there. And we can see we're getting some moment reactions here as well. And now we can also take a look at our critical load factors. So I can jump up here and jump back to our stability, and we can take a look at our first eigenmode here. I can also hit this button here and jump back to our stability and take a look at my critical load factor here, along with my effective lengths for the weak and strong axes. And then if I hit OK, again, I can take a look at my other three eigenmodes here. And you can see one of the eigenmodes is deforming out of plane, or actually all of them are. So maybe something with a moment frame is you would just like to keep it in plane. So to do this, we can add supports to the top corner or corners of our columns here to prevent out of plane deformation. So I could simply just highlight my nodes here, hold Control and highlight both of those nodes, add a new nodal support, make a new nodal support definition type. And basically I want this node to be able, or these supports to, sorry about that, simply keep our supports in plane. So I want them to be able to rotate about all axes or all degrees of freedom. And then also I just want to have them be able to move in translation in the X and Z direction. So I'll click OK. Click OK again, and now those supports are added to the top, keeping my frame in plane. And then I can just run our stability results. And then I can check out my eigenmodes for this frame. So now you can see that my eigenmodes are all mostly staying, for the most part, in plane, and those supports are preventing out of plane deformation. So that basically is the end of the moment frame model example. So now we can move on to the modeling the concrete model. So I'll jump back to the PowerPoint. And this is the concrete model that we'll be modeling. You can see that has a floor slab and then the ceiling slab, which is supported by about 9 columns. And we also have a downstand beam here, which will be our rib member. And we have our surface walls here, along with a rectangular opening in the back. And then we have our spiral staircase that we'll be modeling here with our semicircle slab here as well. And then we also have it supported on the left-hand side here, along with foundation support for the whole entire slab. So before I start that, does anybody have any questions that I can answer within the questions panel. I'll just give a minute for if anybody wants to go over anything before I hop into this example. I'll just start setting up the model real quick. Okay, well, I'll start entering the general data. If any questions pop up, we can discuss them or go over them. So for this one, I'm going to name it concrete model. Training November 10th. And again, description's not too important. You can have it or leave it blank. Everything else looks good. It's gonna be a 3D model. For this example, I'll have a standard selected. So I'll select the American standard, the ASC 716, and I'll create my combinations automatically and have my load combinations created automatically, just to get an idea of what that looks like. And everything else we can keep as default. Make sure our local axes is set to downward. So I'll click OK. And this is our blank grid again for our new model. And so basically, since we activated create combinations automatically, that will create our load combinations automatically when we create our load cases. And again, I'd just like to reiterate that you can change your units and decimal places at any time by going up here to options, units and decimal places. So at any moment or any time throughout your model, you can go from imperial units to metric units by going down here to the load save profile and hitting or double clicking on metric or setting it as default. And then you can change your decimal places throughout these tabs up here, indicating different parts of your model data. So the first thing we want to do is start off with drawing our foundation slab here. So what I'm going to do is go up here to reverse in the Z direction so we can change it. This is handy so we can change our view and get a top-down view to draw our slab. For this model, since it's going to be a larger model, I'm going to change my settings of my work plane real quick for the grid points to change dynamically according to the size of the model. And then now I can simply just draw my rectangular surface like we did before for the continuous plates. So I'll just go up here and click on rectangular surface. And then I want to import my 4000 PSI concrete. And then concrete, and then we can just select our standard, 4000 PSI. I'll click OK. This is going to be an 8-inch thick slab, so we can keep that as default. And then we can simply just draw our slab here, which is going to be 46 feet by 40 feet. So I'm going to start the first corner at the origin again. And then I can look at my coordinates on my cursor and make sure it's at 46 by 40 feet. And I can right click to cancel out of that. And now we want to create the nodes that are going to be the base of our columns. So I'll select this first corner node at the origin. Instead of creating a new node manually, I'll select that and I'll right click on it, and then I'll hit move/copy in the shortcut menu. And then I want to create one copy and move it 2 feet in the X direction and 2 feet in the Y direction. Click OK. And now our column, or our node for our first column here, has been created. And then I want to create 2 more copies of this node for the other 2 columns in this row. So I'll right click on it, move/copy, and then I'm going to make 2 copies of this, and I want it to just be moved in the X direction with 16 feet between it. I'll click OK. And then our 2 additional nodes have been created. And now I just got to create a 4th one. So I'll select this node, move/copy, or I could also just take this corner node here and hold Control and move it wherever I want. So I'll select it, hold Control, and then just move it to be in line with these nodes, and then 2 feet away in both directions from this corner. So everything's symmetrical. And then I'm going to create the second row nodes for the second row columns. And I can use the move/copy tool. I'm going to create 1 copy, and these are going to be moved 16 feet in the Y direction. I'll click OK. And now I have my second column, or second row of columns for my nodes. And now to get a better look, let's say I want to see the numbering for my lines and surface and everything. I can simply right click anywhere, and in my shortcut menu here, I can hit show numbering. And now you'll see the numbering for my slab here. So, for my surface. So I have surface 1, and then you can see the numbering for each of my nodes here. And this numbering corresponds to the tables and also corresponds to the numbering that is in the project navigator over here. So if I click on node 4, then node 4 will be selected up here in the top left-hand corner. And now I want to divide my lines here to create my walls. So I'm going to right click on line 4 here, and I'm going to use my divide tool like we did before. And this one, I'm going to use the method graphically. And then I can simply just go down here, and this will be 12 feet away from the start. And then I also want to do the same thing for this top line up here. And this is going to be 28 feet away from the start. And basically this is making up the line definition for our walls. And now the next thing we want to do is draw another surface. This is going to be our semicircle surface. So what I can do is go here to my rectangular surface button, but instead of clicking on the button, I can click on the little arrow next to it and go down to semicircle. And then it's asking me, okay, material, thickness, this all looks good. So now I can draw this, and this semicircle is going to have a radius of 7 feet. So I want to go 7 feet away from this corner. So that will be at 33. I can click, that'll be my center, and then I'll click and snap to the corner node and right click to exit out of that tool. And now I have my semicircle. And now we can create our ceiling slab. And this is pretty easy because our ceiling slab is identical to our floor slab almost. So the height between our ceiling slab and our floor slab is 11 feet between both of the slabs, but the center axes of the surfaces must have a spacing of 11.83 feet because our slabs have a thickness to them, which is 8 inches. So we want to make sure that the actual spacing between these two slabs is 11 feet, including the thickness of the surface. So I'm just going to take and highlight this whole surface, right click, and use the move/copy tool. Make one copy of the surface and then move it 11.83 feet into the Z direction. And now I have my ceiling and my floor slab, and I can hit my isometric view here, and I can also do a perspective view, which allows me to get a top-down view, and now I can see both my ceiling and my floor slab. I'll turn that off and go back to isometric. And then the next thing we want to do is divide some more lines. So I'm going to go to line 16, which is up on the top here of my ceiling slab. And basically I just want to divide this line in half, and you'll understand why once I divide it, or you'll understand later throughout the modeling process why I divided this line. And then one other thing is, looks like we have our auto connect line /members activated. So whenever a line intersects another line, it'll divide the bigger line here. So it looks like we have our lines already divided, so we don't have to, or connected, so we don't have to worry about that. And now the next thing I want to do is, since the ceiling slab has a different thickness than the floor slab, I'm just going to delete my two surfaces here by holding Control and selecting both of them and hitting my delete key. And then we also want to delete lines 16, 17, and 18. And instead of selecting them graphically, for example, I can go to my lines folder here in my project navigator and then go down here and hold Control and select 16, 17, and 18. But since we had auto connect line /members activated, we only see 16 and 17. So I'll just delete those. And now you can see those two lines were deleted here, and we're left with the center node here. And then also just the outline of our top surface here. And now I can basically just create a new surface using the boundary lines. So if I hit select boundary lines and then change my thickness here to 12 inches, I can hit OK, use my cursor, and the program automatically selects all the boundary lines connected there. And then I can exit out of that tool, and now we have our ceiling slab. And then, since we have that, now the next thing we want to do is create the opening for our ceiling slab, or for our spiral staircase at the top here. So we have a tool for openings right here, and this one is normally set to new rectangular opening, but we have also, if you click on the arrow next to that button, a long list of other shaped openings. So, and you can also create custom shaped openings by using the select boundary lines button. For this one, I'm just going to use a circular opening, and it's asking me, okay, what's the center of this opening? And that's why I divided the line here, so I can select node 33 as my center. And I want to activate the step option here to make each step 1 foot. So now I can easily draw a 6-foot radius opening. And then I can right click, and now our opening is automatically integrated into our surface slab here at the top. Next, Now that we have that created, now we want to create the walls between our slabs here. So the easiest way to do that is just to define the boundary lines that will act for our walls, or that will define our walls. So I'm going to go up here to new line, and then I'm going to draw this line perpendicular to the floor slab. So that's going to be 7 feet away from this node here, which is 7 feet away from our spiral staircase. So that will be at right here. So I'll snap to that grid point, and then I'll draw my line, and I want to make sure it's perpendicular to the ceiling slab. So you can see, it's kind of hard to see right now, but you can see there's a red dot there, and then there's a little symbol telling me that I'm perpendicular to the slab that I'm connecting to. And I can snap to that just like in AutoCAD and right click to disconnect that line. And then basically I just want to do that same thing from here. So that's going to be, that line is going to be 12 feet away from node 3. And that will be at this location, 3440. And then again, I'm going to snap to that perpendicular point, right click or left click, and then right click to disconnect the line. And then I just want to do that same thing for 20, for nodes 20 to 40, and for nodes 16 to 32, 3 to 19. Actually, that one doesn't look, yeah. Control Z to undo that. So I'll select my line tool again. That'll be 3 to 19. Disconnect the line. And then I want to draw a line from, let's see, 14 to 30. And 4 to 24, or 4 to 20. And then the last one will be 13 to 29. And now you'll see why we divided our lines there, to get these nodes so we can connect our lines and create our walls. And now we can create our wall surfaces since we have our boundary lines. So I'll go up here to select boundary lines. And then these walls are going to be 8 inches thick. I'll click OK. And now it's asking me to select the boundary lines for these walls. So I'll simply just go around here and make sure that I select the lines in a polygonal chain. And so now I can create this last wall here right next to my spiral staircase. Right click, and now we have our vertical walls here. And now to create this curved surface here for our spiral staircase, we have to use a special tool. Since this wall will not reside in one plane, we have to use our quadrangle tool. So if I go up here to this button and hit the arrow next to it, I can find my quadrangle tool, general four-sided surface. So I'll select that, and this is also going to be 8 inches thick and the same 4,000 PSI concrete. I'll click OK, and then this is just like selecting the boundary lines for the walls. I'll select those boundary lines, and now we have our walls and also our curved surface. And to get a better look, I can change the rendering to a solid rendering just to get a better idea what that looks like. So now we can move on and we have one more wall to create, which is our inner wall, one of our load bearing. It's going to be a load bearing wall. So what I need to do to draw this inner wall here is I need to change the origin of my model. And to do that, I can go up here to this button, very easy, called set origin of grid/work plane. I'll click on that, and then I'll just tell it, okay, I want it to be at node 14. So now my new origin is at node 14. And then I want to draw this wall and the YZ plane. So I'll set my work plane to the YZ plane. And now I can simply draw my wall right here. And so it's going to be a rectangular wall. So I'll just go to my tool here, rectangle. This wall is also going to be 8 inches. And so I'll click OK. And the first corner is going to be at node 14, and the last one's going to be at node 26 up here on the ceiling. And so now we have that load-bearing wall right here. And we can set our grid plane back to the XY plane. And now we can go and create our columns. So since we already have the nodes set for the location of our columns, all we have to do is connect them. So I can just use my new line tool and connect my nodes here. I will connect nodes 5 and 21. Right click again, and now I have this line here, but it doesn't have any cross section or material assigned to it, so I'll double click on it to edit it. And then I can go to member, and under the member tab, I can go to available and check off available for the member option. And then I want to just import a cross section from the cross section library. And this will be under the parametric massive, and it'll be a rectangular cross section. And the base of this one is going to be, or the dimensions of this column are just going to be 14 inches by 14 inches. So it'll just be a rectangular column, and my material will be 4,000 PSI. So I'll click OK again, and then one more time. And now our cross section, or our line, turned into a cross section with material. So now, instead of having to connect these all and do that again, we can use that same workflow that I talked about, that I've been talking about with the control. I'll select this node here, hold control, and then drag. And I need to select the column as well. So hold control, the column selected, and then drag. And I can make a copy of that. And then I can continue for doing that for the rest of this row. Take that and drag it. And now we have our columns created. And there's another tool that I would just like to show you real quick that's called Select Special. So if I go to this tool, and let's say that I have a lot of 14 by 14 columns, all in different locations, and they're very hard to highlight all of them. I can go to Activate Members and check that off. And then I want to select all of the cross sections, all the members with cross sections of 14 by 14. And I'll click OK. And now all of my columns here have been selected. And what I can do is utilize my control key again, hold that down, left click, and then just simply copy that whole column. Whoops, I didn't copy it, but if I hold control and then click and drag, let's actually Control Z, undo that. I want to hold control and then copy. There we go. You don't want to click and then hit control too fast. So now we have our columns here and our columns and our walls created. And now finally, we just want to copy our last column to our node back here. Looks like I am missing a node, so I'm just going to take this column, hold control, copy, and move it back. There we go. So now that we have our columns and walls created, now we just want to create our downstand beam that's going to connect from node 29 here to our load-bearing wall, and then to our column here, 42. So it actually looks like our load-bearing wall is extended too far. So what I can do is simply just back it up some. I'll create a line here from node 20 to 42. And then I will select my wall and then just move it back some. Although I took my column with it. There we go, and then I can just move that back there. And now we can create our downstand beam with this line here. So I can simply just hold control, double click on it, and then I can use this general tab here, member tab, and choose available. And then with my member type here, this is where we're going to switch the member type from beam to a rib member type. And basically a rib member type, you'll see, has extra options or settings here. So we need to edit our member type for the rib. And basically what a rib is it integrates or it turns into a T shape and integrates into the slab, the concrete slab, and also keeps the rectangular member that we've created. And we want to make sure that that rectangular member is on the positive Z side of our surface. And we also want to tell the program, okay, what is the width of the integration of each side of this T shape into the slab? And we want that width to be length divided by the length of the member divided by 8. So we'll select that, make sure it's on the bottom side of our slab here. So we'll click OK. And now that we have all of our information filled out here, we also want to change our cross section. So I'm going to go to import from cross section library. And then I'm going to go to parametric massive. And basically this rib is going to be 12 inches by 12 inches. And it's going to have a material of 4,000 concrete or PSI concrete. And then I'm going to click OK again, and again. And now our rib member here has been created and is integrated into our concrete slab. And you'll see the rendering. You won't be able to see the T shape of it, but you will see that the beam is dropped down about, and an eccentricity is applied, and it's dropped down to the thickness or half the thickness of this top slab here. And now the next thing we want to do is create the opening, the rectangular opening in the back here on our wall. And to do this, we can use our rectangular opening tool, but we also want to set the origin of our work plane. So I'll go up here to set origin of work plane. I'll make it this bottom right-hand corner here. And then I'm going to change my work plane to the XZ plane. And I'll go up here to my openings tool and go to the drop-down list and hit rectangle. And then this rectangle or this opening is going to be, it's going to be 9 feet wide and 5 feet high. So I'm going to draw it from 1408 down to 503. Click, and now we have our window here and our wall. And then I can just set my work plane back to normal. And now the next thing we want to do is add supports to this structure. So for this example, I can assume that due to the foundation, we can assume there's going to be an adjacent building to the left of this model or of this building. So we can assign support features to the line right here. So if I just click on this, or click on both of these lines and hold Control, I can select both of them, and then I can go to New Line Support. And this line support, I will create a new line type. And for this one, the only thing that it's going to support is the vertical direction. So that'll be translation in Z. Everything else can rotate and everything else can move except for the Z direction. So I'll click OK and click OK again. And now our line supports have been added to support this whole entire left side of the foundation. And the next type of supports we want to add is for our slab. So I'll double click. I can add these surface supports to my slab here, to both my slabs, the circle or semicircle and the rectangle. I'll select the rectangle, hold Control, and then select my semicircle. And then I can hit right click, hit edit, go to edit surface. And then under support / eccentricity, I'll check off available for supports. And then I will keep none of these fixed. So I'm going to keep these unchecked and nothing will be fixed, but I will add spring constants. So I will add 64 kip per cubic feet for the X and Y direction. And then for the vertical direction, this will act as the shear capacity of this will be the foundation modulus for the gravel. So it'll be 640 kip per cubic feet. And then for the vertical direction, we can set a nonlinearity. So I'll go here to the dropdown, and we want to select failure if negative contact stress in the local Z direction. So basically what this does is this corresponds to failure under tension. That is, if the slab is lifting, if it's lifting up, then no more support will be provided to the slab. But if it's being pushed down, the supports will support it. Then all we want to do is add some spring constant for the shear in these planes. And then I'll click OK. And again, and now we have our surface supports and you can see that they are blue. If you see a blue support, this means that the support is a nonlinear support. The next thing we want to do is add some stiffness modifications. We talked about this earlier. So I can simply just highlight from right to left, basically highlighting all the walls and the columns. And if I right click on any of these elements, you can see since I have multiple elements selected, I have surfaces, lines, members, openings, nodes selected. I basically just want to go to members, which are just my columns. And then I want to go to edit. I could have also just double clicked on the columns to edit them. Go to modify stiffness. And then under definition type, since we're modeling, or the structure would be for this example modeled according to the ACI, the American standard, we can click on that. And then the component type is columns, and our multiplication factors are taken automatically from the standard, so we don't need to worry about entering those manually. So we'll click OK. And then we can do the same thing for our walls. So if I just double click on my walls here, we can go to modifications or modify stiffness. Definition type, I'll choose the standard. And this one will be walls uncracked. Then that modification factor will be applied. So I'll click OK. And then we can do this for our plates and slabs. So I want to select my ceiling and both my floor slabs here. An easy way to do this would be to go to the project navigator and then going to surfaces, expanding that and choosing planes 1, 2, and 3, and then right clicking and editing them. And then I can go to the modification tab, modify stiffness tab, definition type, and apply this for flat plates and flat slabs. So we'll click OK on that. And now lastly, we would want to do this for any of our beams, aka our rib member. So I'll select that, edit the member, and then go to modify stiffness. And then I'll choose my component type as beams, the multiplication factors will be applied, and then I'll click OK. And now we modified the stiffness of our entire model here. And now we can get into our load cases and combinations. So just real quickly, since looks like we have about 7 minutes left, I'll just go over this in 2 minutes real quick, so I can leave some time for any discussion that anybody would like, and if there's anything we'd like to discuss or any questions, we can go over them. So basically, we don't have any load cases created right now, but if we did, we could create some real quick. We do have we created our dead load. So if we had a dead load, and then, so we'll just name this dead load. And you can see that the action category was set. And then we could go down here to this button called create new load case. And we could name this one live load and change the action category to live. And then we can create another new load case. And this one would be wind and positive X. Change that category to wind. And you can see for the live load and wind load, self-weight's not activated. For the dead load, it is. And then we have our actions tab, categorizing our actions according to the standard we selected. And then according to our standard, we'll have our combination expressions and then our action combinations generated. And if you want more information on what these which ones are generated, we can click, or how these are generated from the standard. You can click on this eye here and it'll give you this information from the standard. And then our load combinations for both serviceability, limit state design, and our ultimate limit state design have been created here as well. And then basically we would have our result combination, which is an envelope solution taking the worst case scenario and best case scenario from our generated load combinations and putting them into and giving our maximum and minimum results for each of those categories. So yeah, so that's basically the end of this example and almost the end of this training. I just wanted to leave some time just in case anybody we can hop back to the PowerPoint. I just wanted to leave some time just in case there was any questions that anyone had or anything anybody would like to ask before we end the training or anything we would like to go over. So while we're waiting for any questions that come in, I would just like to mention that again, the models of this training, this training was recorded, and the certificates will be sent out through email after the training. And again, you should see these items within the next couple of days. There's also a survey that will pop up after the training ends or after the webinar ends. And we would greatly appreciate it if you could fill this out and give us some feedback. That would be awesome. Again, you can ask any questions. So is it possible to add wind loads to the model? Yeah, so adding wind loads to the model would just be adding, here I can go back. Basically, that would be just adding member loads, and surface loads. So if I wanted to, let's say, add a lateral load here, we could do that. Looks like my load case isn't saved. So we could just click on this button here called surface load. And let's say our load case would be wind in the positive X. And then I could simply just, the new surface load dialog box will pop up. And you can tell it, okay, I want to apply this surface load in the global Y direction. We'll just give this a quick magnitude, click OK. And then I could just simply add those surface or those wind loads in, but I would add them to the back end of the structure. Like so, once this loads up. So like that, this would be more of a suction load, but I think you probably understand the idea. Are there any other questions? Will there be a part 2? On the site it shows 2 part 3s, or 2 part 3s. Yeah, so there's only one, there's no part 2 or part 3 to this training. I think this was the last student training for this year, but I'm sure we'll be giving more next in 2021 and the beginning of next year at some point. So yeah, look out for those, but there is no part 2 or part 3 to this training. So
it looks like we have one more question maybe before we end. Can we design a roof slab with a down beam? I believe that's just a slab element with a downstand beam or maybe a rib type element. So maybe you can just explain eccentricities quickly.
Yeah, so that's kind of like the rib member we designed for this ceiling slab. Is that correct? So you could, instead of using a rib member, this could just be a beam, a normal beam element. And so let's say if I just take this rib and turn it into a beam, you can add eccentricities to drop the beam down below the ceiling slab. So if I'm in my edit member dialog box here and go to options and then under member eccentricity, I can create a new one and I can tell it, okay, offset my beam, or take the top of it and offset it to the bottom, do a relative offset. And you can also do a manual absolute offset, but you can use this to add an eccentricity and drop it down below the ceiling slab. So yeah, I think it looks like is that the last question? Yeah, with the down, okay.
Yeah, that looks to be the last question.
Okay, yeah, so yeah, this is the end of the training, and I would just like to mention just a couple more things before we end real quick. Is we have some free online, oh, I'm probably showing the wrong one, sorry about that. Yeah, so we have free online services such as our GeoZone tool, along with some cross-section properties. We have FAQs and knowledge base articles, which are fantastic for if you're a new user and you're learning RFEM and you have some questions. I would always search in those to see if your question has been answered. We also have a lot of different models you can download and take a look at. A lot of cool models on our website to take a look at. And then we also have our YouTube channel with webinars and videos, our web shop, and trial license. I'm sure you already have the 90-day trial down, or for students, you get your free license, so you don't need to worry about that. But definitely recommend the YouTube channel and webinars and videos. These are very helpful, and Amy gives some fantastic webinars that are very helpful in learning the program. And there's also great webinars for more experienced users if you would like to take a look at those. And then again, our website, and then we have our phone number down here and our tech support email. If you have any questions, you can give us a call or send in an email to us. And that's about it. So thank you so much for attending, and everyone stay safe and have a great rest of your day.